So hopefully by the time you're watching this video, you're familiar with the sine function. Right, you know, the sine function, it's maybe hard to see, it's this black wave here. And you might say, okay, well, sine's difficult, right? So if I was trying to do this, maybe I didn't have a calculator, maybe I didn't have some sort of modern computing device and I wanted to calculate a sine function. What I might do is I might say, well, if I get something that kind of looks like a sine function but is a polynomial, it's easy to evaluate that, right? So if I want to take sine of 2, for instance, that's difficult. You know, I'd have to plug that into a calculator. But if I had a polynomial function, something like, you know, something x squared, I could just plug 2 into that. That becomes 4 times whatever the coefficient is and whatnot. So what I might try to do is take this, and this is this little green curve here, and try to approximate the sine function, you know, kind of near that pi over 2 point. Maybe that's kind of where I'm concerned with. And that's okay. You know, notice it gets pretty bad here, right? You know, it gets pretty awful. So then I say, okay, well, maybe I'll do a cubic function. That won't be too bad. So a cubic function comes up. Maybe it's, you know, and you could get it to kind of be tight here so it matches exactly. And you could get it to be tight so it matches exactly there. But if you do that, these arrows are also going to shoot off, and they're not going to be very, this might be okay through the origin, but then it's going to eventually degrade, and then this is going to shoot off. So then you might say, okay, well, I want, you know, a quadric function, so, you know, keep going, and so on and so forth, right? And the idea is, okay, well, once I do that, you know, how many terms do I need? Well, what some guys developed, I mean, this is, you know, hundreds of years ago, is a systematic way to do this, because, you know, if you think prior to the way that we did things on calculators and whatnot, there was no easy way to evaluate a sine function. And in fact, the processes that we're going to learn here are still in practice today to develop some really fast approximations of things like sine functions. Even though we could just tell a computer to do it, it's actually relatively slow for a computer to calculate sine versus calculating something like a polynomial. So there are still modern practices for this sort of thing. So anyway, what we can say is that for a lot of functions, and there's a term that it gets thrown around, you'll hear it's analytic is the term. It's not always true, but usually that means it's related when a function can be differentiated an infinite number of times. That's not 100% true, but if you can keep differentiating it, just keep going and going and never have an undefined derivative, then a lot of those functions are analytic. And so anyway, we can approximate the polynomial. Now what we're going to do is we're going to pick a center. The reason why is because if you see this curve here, it approximates pretty well, but if we had like shifted the approximation here, it might approximate this curve well, but it would approximate that poorly. So what we really want to do is say, okay, where do I care about evaluating values the most? You know, and you notice like for a sine function, if you can get it to approximate one period pretty good, you can actually cheat, right? You can always take a value outside that period and shift it and then use the polynomial approximation. So what we do is you pick a center. And what we're going to do is just define a polynomial. So it's some number, right? So that's like your constant or a vertical shift term. And then there's a coefficient times x minus c. So this is a linear polynomial, right? Like in a straight line. And then another coefficient times a quadratic. So that would be your parabola. And then you could keep going. And you could go to some arbitrary. You know, I might say I want a 10th degree polynomial. So then what you're going to have is this term, which is some number times x minus c to the 10th power. So this is your 10th degree polynomial. But you need all these other terms here, because what you're going to want to do is you're going to want to say, all right, I need to figure out what these numbers are. Because these numbers right here are going to be sort of the anchor points of how this thing, you know, how does it match the actual values of the function. Which is, I mean, if you look at this, you go, okay, well, if I plug in c, that's easy. If I plug in just the value of interest, that center point, all of these disappear. So this first term is just the function value. It's just the function value. So if this was centered at pi over 2, this would be whatever sine of pi over 2 is, which is 1. So this would just be 1. But what about for the linear term? Well, I can't just plug c in because, you know, I've got all these. So anything that would make these disappear makes that disappear. So how do I come up with a convenient way to solve for what a is? Well, I have a polynomial. This is a polynomial. So I know through calculus what its derivative is. If I take its derivative, I'm turned around. This a0 term disappears, right? Because the derivative takes care of that. And the derivative of this is just a1 because it's a1x, which is the derivative of that is a1, and then a1 times a constant there, the derivative of that is just 0. So the derivative of this is a1, and then you have all these other terms. So if I plug in c to this function, it gets rid of it. So what that tells me is I can, since this polynomial is supposed to approximate the function, I could take the function's derivative, plug in c, and that would give me what I would get for a1. And then if you take the second derivative, the a1 term disappears. This becomes 2a2. And then this derivative doesn't just become 3, it's like 3 times 2. So we're getting kind of some chain terms because of the, you know, the repeated differentiation. And then you have this n and then n minus 1 here. And if you keep going down all the way, so we were talking about a 10th degree polynomial. So if you go down to like the 10th derivative, what you would have is 10 times 9 times 8, 7, 6, 5, 4, 3, 2, 1, an. So what you really have is 10 factorial. So by doing that, what we're doing is we're finding ways to isolate each individual term of that polynomial, which is kind of neat because what it allows us, it gives us a systematic process of saying, I need to solve for what these are. I can use calculus to take derivatives and then plug in the value at c and just obliterate all the other terms. Now, I do want to point out something important. In the case where c is equal to 0, where that center value 0, it's a really nice approximation because now I don't have this x minus c, I actually just have x's. So, you know, that's a lot cleaner, right? And then when I take my derivatives, I just plug in 0, so it blows out everything that's not your leading term. And this is what's known as a Maclaurin polynomial. This is what's known as a Taylor polynomial. So they're related. Maclaurin polynomial is just a special case of a generalized Taylor polynomial. So if we look and we see, all right, what's the pattern here? The pattern is that our first coefficient is just the function value at that point. Our next coefficient is the value of the derivative of that function at that point. And I have it written by divided by 1 factorial because that's just 1. So that's that right there. The second one is the value of the second derivative divided by 2. Now you might say, okay, well, what do you mean divided by 2? I have this here. Well, that's true. When you wipe all that out, you actually have to divide over by 2 here to isolate what a2 is. So that ends up being 2 factorial. In the third case, we don't have the third derivative here, but it would be like this term. It's going to end up being this term, 3 times 2, a3. So that's 3 factorial, 3, 2, 1. So it's the third derivative evaluated at the center point divided by 3 factorial. And the general case is that the nth term, so this could be 1, it could be 5, it could be whatever, is the, and this is something you may not have seen before, which is the nth derivative. So this is kind of a notation that is very common, but you may not have seen it before because there hasn't been a lot of need for you to see it until now, is that the sort of superscript, the number will be in parentheses there. But if it's like it's not in parentheses, sometimes that's like an f squared, you know, like if it was f2c, sometimes like f squared c. But if it's in parentheses, that usually indicates the nth derivative. So if that was a 4, that would be the 4th derivative evaluated at x equals c, and then divided by 4 factorial if this was a4. a4 would be the 4th derivative evaluated at c divided by 4 factorial. So if I have that, so no, again, following this logic here, if we take this polynomial and then we use this term, we have the function value f prime at c times x minus c, f double prime at c divided over by 2 factorial times x minus c squared, and so on, all the way to the nth derivative evaluated at c divided by n factorial times x minus c to the n. This actually condenses into something that looks like this. I start at k equals 0 and I go up to n. Well, let's think about this. Let's think about this for a moment. In the case where k is 0, so in the starting version, you have 0 factorial on bottom. 0 factorial is just 1 if you've forgotten. And then I have the 0th derivative. Well, yes, you have the 0th derivative. That means you are not taking a derivative. So the 0th derivative is just the function value, which is this. And then you have x minus c to the 0 here. So that's why you don't have any sort of x minus c here. Now in the case where k is equal to 1, you have the first derivative divided by 1 factorial, which is f prime at c, times x minus c to the 1. In the case where k is 2, you have the second derivative at c divided by 2 factorial, x minus c squared, and then so on and so forth. And so what this allows you to do is set this up in a series notation. And you might ask yourself, why are we doing this? And you might then think to yourself, well, we've been doing a lot of things with series, but we haven't been doing things with finite series. We've been doing things with infinite series. And so that should sort of tip off something in your mind about where we're going with this and kind of where, what we might be trying to do and what we might be trying to apply to achieve some really interesting results.